Customization techniques for text-to-image models have paved the way for a wide range of previously unattainable applications, enabling the generation of specific concepts across diverse contexts and styles. While existing methods facilitate high-fidelity customization for individual concepts or a limited pre-defined set of them, they fall short in achieving a scalability, as adding new concepts or combining multiple fine-tuned models without incurring additional computational costs can be challenging. A naive training-free method for combining multiple customized models is to take the average of each model's weights. However, this leads to loss in fidelity of each custom concept. For instance, consider a model that was fine-tuned on a few images of a specific pot. On its own, this customized model can generate images that closely resemble the reference pot. However, if we naively merge this model with another model customized on a different concept such as a dog, attempts to generate the original pot using the merged model results in a significant loss of fidelity. We call this problem crosstalk, as custom concepts interfere with one another when combined into a single model. Our solution to crosstalk is to disentangle each concept by enforcing orthogonality in their weight space. We simplify the weight space to 3 dimensions to visualize this at a higher level. Without enforcing orthogonality, taking the average of each model's weight results in a poor representation for every concept. By enforcing orthogonality, represented in this diagram by placing each model on a different axis, the resulting average is a much more informative representation of each individual model. We explore this idea in a more mathematically rigorous context in the published paper. Next, we will dive into how we achieve orthogonality in weight space between individually customized models. Our method builds upon the popular LoRa technique for parameter-efficient fine-tuning. LoRa freezes the original pre-trained weights in a model and instead only fine-tunes a set of low-rank decomposition matrices injected into each layer. Here, for some custom concept I, the result of the fine-tuning procedure are 2 matrices AI and BI. We refer to the product of A and B as the training residual. Similarly, our method keeps the original pre-trained weight matrices untouched, opting to fine-tune for a set of decomposed matrices. However, in our case, we choose to freeze the B matrix, and only let the A matrix be trainable. Here, we show the fine-tuning results for 2 custom concepts and their respective output matrices. The goal now is to ensure that the training residual for both concepts are orthogonal with respect to each other. We opt for a simpler objective. A sufficient condition for both residual matrices to be orthogonal is for the B matrices of each concept to be orthogonal. Note that both concepts are fine-tuned individually, with no knowledge of one another, making the process of enforcing orthogonality non-trivial. To address this, we introduced the basis sampling method, a method for achieving approximate orthogonality between concepts during independent training. The basis sampling method works as follows. We first define an orthogonal matrix which is shared amongst all users. Note that by definition, any 2 columns of this matrix are orthogonal with respect to the other. We then define BI by picking R random columns from the orthogonal matrix, where R depends on the dimensionality of BI. We do the same for BJ, also picking R random columns from the orthogonal matrix to populate the columns of BJ. Observe that the columns of BI and BJ are orthogonal unless they collide, and due to the high feature dimension of the weight matrices, the probability of collision is kept low, meaning BI and BJ are approximately orthogonal with high probability. We evaluate our method on the task of identity preservation, measuring a model's ability to generate high-fidelity images of a custom identity before and after merging. Quantitatively, our method achieves state-of-the-art results in image and identity alignment metrics after merging, highlighting our method's ability to overcome crosstalk between individual customized concepts. Merging is also instantaneous, as it is simply done by taking the average of all model weights. Compared to relevant baselines, our method, shown in the top left, is able to render target concepts at higher fidelity, whereas other methods show a significant loss of identity. Finally, to further demonstrate the efficacy of our method, we trained a bank of individually customized models using our method. We then picked a random subset of these models, merged them via summation, and generated the images shown. For more information on this project, please visit our website and poster. Thanks.